pointed out Please continue. So I will start from here. So further evolution of these T Tauri star class 2 sources, they becomes totally unveiled from the outer envelope, and this disk has the accretion from the disk almost stops, and these systems are known as big T Tauri stars. Those are class 3 stars. Further evolution of this that creates a full phase system of stars with planets surrounding around it. So the process of mass accretion in these stars has a certain evolution. The tentative plot of log of mass accretion as a function of the age is shown here as because of outbursts they appeared in the optical, and we can study these sources in the optical and other wavebands. So these phases of sudden mass accretions provide a very good phase of understanding of how these low mass stars gains masses. So this is the particular phase where I'm interested, and I have my object is around in this source, around in this phase. So the motivation is that since these phases of high mass accretion rate, these can be observed in even in the optical, we can observe in various wavebands, and we can better understand these sources. How do they accrete mass? And one of the other motivation is that since these phases gives a good understanding of the mass accretion rate, and there are very less number of such known objects categorized and understood objects. So any object, if we found, the understanding of each and every object is very important. So what my object is, since one of them I have chosen it to study. So here is the nebula LDN 1415 nebula. So the thing is, sometime in 2006, Steplam and his colleagues doing a survey of Herbig-Haro objects in the Lens cloud, and they found an Herbig-Haro object HH892A in an opacity class 3 Lens cloud. The cloud was named LDN 1415, and the follow-up observation of that Herbig-Haro object, since these objects are expected to be associated with young stellar objects. The follow-up observation, they found a nebula here, right? As you can see. Okay, so as you can see, this is a post image from the 1990. There is no as such object here, but right here, this is a H-force image, not from the Steplam image. This is we see a certain sort of nebula. Since this object last was observed in 2001 in a KISO I-band image, and then later it was observed in 2006 only. So it is expected that in that period only this source went into outburst. So there is an uncertainty of almost 6 years. When the source was observed, it had brightened by a almost 3.77 magnitude in I-band with respect to the KISO I-band. So the basic parameters of this LDN 1415 nebula is it is an 4-hour source, and it is situated in northern hemisphere at a 54 declination angle. It is expected to be at a distance of 106 70 parsec, there is uncertainty in the distance of this object. I'll talk about it at the end a little bit. In the field of view of this object, in a thin archinate field of view, there is only one iris source object, and that iris source falls within the error ellipse of this particular nebula. So it is expected that that iris source will into outburst, and hence that the source of this nebula is named as LDM1415 IRS. So a long observation has been done for this object under a program of monitoring exoranus sources program, which you talked about earlier. So the observation of this source was done from 2006 to 2013 from IGO in the Ayuva Birabali Observatory and this at 2 meter SCT, and there were several some NIR observations done with the NIRCam attached on SCT, and there were few of the optical spectra on optical spectra accounted observed from the H-force. Some archival images have been taken for the references and for calculations, that is post 1, post 2, 2 mass, KISO, ZTF, and the vice archival study, archival data. So I will show some of the initial results and that analysis that we have. So for the first thing to start with, I have shown the morphology of the particular source. If we see in the optical, this the first image, if we see this first image, this is the first image that was taken with the H-force. Just when Professor Oja started following this source, in this source we can see a very bright nebula that I showed, which appeared out of nowhere. There is a little beacon which I will talk about in a moment. After some time, when this optical nebula faded, it turned into a arc shape. That arc shape is has been described as the viewing of the angle of viewing of the lobes that is created by the outburst of these young sources. During outburst, they create a lobe, and having a different viewing angle, we can see a different morphology. Although this morphology depends on many of the other parameters, like the configuration of the cloud and viewing angle and many other things. While looking at this particular region in H alpha band, we see clearly two Herbig-Haro objects. This is sort of turning way back, like since because this particular nebula was observed after having an observation of Herbig-Haro object. The morphology completely changes when we turn into an near infrared. Suddenly things start changing. So I have shown here only 3 images. The first one is Tan-SPEC. Tan-SPEC image is a very recent image taken on the 14th of January. This very year, we see clearly 2 sources, and this completely changed the view that we were having for 4 months, 4 years about this source. There is T-SPEC image because of low resolution with respect to that of Tan-SPEC. Clearly, if we have inference, we can say that there are 2 objects, but they are blended. Just to get a sense of like this source went into outburst, I overplotted the NIRCam, this T-SPEC contours onto the H-force carband image, and sort of, if we see the optical peak of the this nebula sort of coincides with the northern source. Northern source means the upper source, which I will call the northern source. Source of coincide the 2 sources, and we expect this particular source to be the LDM1415 IRS, and this went into outburst. This is our inference. So what these 2 sources are? If we see the 2 mass images in the JHK band, there are sort of like we can have an inference that there are 2 sources, but clearly they are not resolved because of its resolution. If we neglect for a moment their error in photometry, the difference in the color of the 2 sources in H and K band is 0.35 for the 1998 2 mass image, and from the current understanding from that of Tan-SPEC image, this H minus K color for the two objects has a difference of 0.04. The latest color might have can have a lot of not lot of but sort of some photometric error. So owing to the errors, this says that the colors of the two sources are almost similar. This tells that these sources must be from the same region and they might be connected in some way. So I have shown the light curve of this source in the VRI try of the optical wavebands. This clearly after the outburst, I mean of first observation in by the speculum, that those red points, those red squares, the source has continuously been going into a quiescence phase. In between this gap, we don't have H-forced observation or any other optical observation from our own observation. Here, the black dots are black stars are the JTF images. So, from analyzing these three or the type of the wavebands, we see clearly that the source has been going into quiescence with almost the same rate. The rate varies at the third order. The amount of magnitude that the source has declined is 1.5 in V and R band and by 1.45 in I band. If we go into NIR, again in NIR we have a very less epochs of observation, only 9. The red dot shows the two mass location, and this blue stars shows the near cam observation, and this black star shows the recent telescopic observation. So clearly, from this 2000 almost around the 2008 observation, 2007-8 observation, the source went into outburst in near infrared band also, and from there the source has been, we can get an inference of, has been in the declining phase. The dimming of the source, as we can see from the from this sort of table, that the source is diminishing, but it has not gone to its pre-outburst phase. The NIR color plot shows can tell us something about the source. This red dot again shows the two mass location on this NIR color plot. From this red, this two mass location, the first NIR observation brought the source almost down by 5 magnitude in AB. So this tells that a source, the combined effect of source and the cloud, that amount almost AB is equal to 5 magnitude amount of material has been depleted in between the line of sight of us and the source. And after that, these stars, these locations, the first observation of NIR, the source started returning back to its almost the pre-outburst location, and these are the current telescopic observation, and it seems like the star has almost returned back to its location. One thing to be remembered is this is not the color diagram for the star only, because in NIR we have in NIR and optical we have been doing photometry at 10 arc-second aperture, and that 10 arc-second aperture includes the both of the sources in NIR and the whole optical nebula in the optical. So any effect is a combined effect of the nebula and the source itself.
Question, just to follow. Can you just take us through the chronological order?
Okay.
Just quickly.
Okay. So this two mass, then this is the first. This one is the first, second, third, and the fourth one is expected to be an error.
Show there.
Okay, this is the fourth one, and it is expected to be an error. Even this T-spec is expected to be an error. So there is a catch, like we wanted to have this source went into outburst. So if we look the chronological way of these observations, starting from the two mass in the 1998, the near cam in 2007, the telespec in 2021, and the telespec in 2022 January.
So this is the box you have taken the aperture.
No, this is not the box. This is just to show that these sources are there.
So
I have not shown the box.
So how big is that box?
So that
combined.
that includes both of the sources. I mean, So actually the box was taken in order to include the whole of the optical nebula, that of 10 arc-second, and from that it includes these two sources also. This red, this circle shows just the common star, common location of stars in some of the images. So we see from the two masks that the two sources are blended in the near cam. If we have inference again, we can see that that one of the sources that I'm calling the northern source is sort of an outward, has enhanced my brightness. The lower one is again sort of a blended. In telespec, we got some inference that there might be some source, the two sources, and in telespec clearly the follow-up observation of the telespec. So the two objects are clearly detached. Again, this northern one which we are expecting to be the outburst source. The southern source, southern means the lower one. Its nature has to be understood. So in order to get a better understanding, this was
All those resolutions are same?
no, obviously no. So two mass is having a resolution of roughly 1.5 something, and
The last one?
Huh?
Last one.
the telescope one.
Yeah.
So it is
Right,
having a
right.
resolution of 0.8 to roughly 0.8 arc-second. As a sort of
No,
so in order to get better understanding of this source wind into outburst, what I did, I brought this near cam image into the same scale, the resolution and everything, with that of two mass, and I then subtracted this two mass image from the near cam image. Then I overplotted the contour of the subtracted near cam image minus two mass image onto the two mass image, and here is the result. So clearly, the contour of the subtracted images is on the northern part. Here, the morphology will be changed because of the way that images are shown. Basically, the image has to be flipped, and the southern source here, the below source is the northern source, which we are expecting to be northwest. So this is a prominent reason to follow that the northern source has went into outburst. Here I have shown some of the spectra taken way back in 2007. Again, from looking at the spectra, we can't say that any prominent feature we have here. But again, I have tried to put some of the important lines. And if we zoom in like this H alpha line, again there is not as much confidence in this H alpha line. If we zoom in this H alpha line, we can see that we can get an inference of that there is an H alpha line in the left hand side I have shown. Meanwhile, I have shown here in the right hand side, this is a cutout from this speculum paper, the person who has observed this source for the first time. So his spectral source enhanced pre-Cygni profile and H alpha profile, which gives an inference that outburst was just not an effect of dust clearing or anything, but also it includes the accretion basically. And P-Cygni profile indicates some of the wind flowing towards us. Unfortunately, speculum didn't calculate the wind velocity which he could have by looking at this P-Cygni profile of the H alpha. Again, at last, I would like to present this Harvey-Harrow object. Because this was the initial point for the discovery of that nebula. So clearly, the two Harvey-Harrow objects were seen, and the two Harvey-Harrow objects, HH892A and HH892B, they are aligned with that of this portion of the source, this portion of the nebula, where we are expecting to be the source to be there. This aligning and then follow up spectra of the two Harvey-Harrow object and their radial velocity measurement having a very less difference tells that this axis of flow is on the sky plane. The radial velocity of the two radial velocity measurement from the spectra of the two Harvey-Harrow object were having very less difference. So this gives an inference that this source, the axis of the source is on the sky plane. So again, the source has to be categorized and in order to understand it much better. So here what I have done, I have taken this WISE 22 micron image and overplotted on this spec image again to get an inference which source window into outburst. And we can see that the northern source will coincides well with the central contour of the WISE 22 image. To get an inference which class this source belongs to, I have used this categorization method from the WISE from this conic paper, and this source falls somewhere in the class 1 source. We expect it to be again the speculum did this spectral energy distribution analysis, not analysis, but he just plotted and based on the slope of that SED, he also had reported it to be in class 1 source. Again, whatever analysis has been done so far, it included both of the sources, and in the optical, it included the optical nebula also. So all of the analysis has to be done once again when we have the PSF of the this star in optical by using some image manipulating technique, and in the NIR we have to take more and more telescopic observation in order to get the two sources detached. The possible nature, again, it may be an XOR type of sources, the amount of magnitude is built into outburst, but there can be uncertainty because we have been including both of the source so far. So in the summary of my talk, I have reduced 108 datasets, 78 optical H-FOST and I-FOST datasets, 9 NIR datasets, 3 alpha H-alpha datasets, 3 optical and 15 ZTF datasets. Again, and rest of the things are what I have talked throughout the talk. And I would like to thank some of the people like my supervisor and Joe and Supio for helping me throughout this work, and to the Mank for some of the help, some of his help during the development of some semi-automatic pipeline which I developed for the.
Okay, thank you.
Thank you.
I'm just curious about this class 1 that you have got, because although the peak of the WISE is there, there will be contribution
Yeah.
from the other source.
Yes.
So it may not be very appropriate
Yes.
to categorize it as class 1 based on the WISE color
Yes.
itself.
So
Now,
that
so
is what
the WISE 22 micron
Yes.
has code
that
to
bigger
be-
block, right?
I mean, even
So-
otherwise it is 12 arcs again. Even if you take the 3.6
Mhm.
and all, the resolution is very poor.
Yeah, so I would like to say one thing regarding that. This particular image, I had overplotted sometime way before when I came to here, and I tried to get this WISE image and overplot it on the overplot the TSPEC image, but I was not able to connect to my this PC where this TSPEC image
No,
is.
no,
The problem, another thing is,
no, the visualization of WISE 22 micron is
Hmm.
very coarse
yes,
and is bigger than your difference between the peak of two
Yes.
sources.
so again, this is this
So the
classification.
other source will also be contributing to the flux. So
Okay.
if you cannot use that to
Yes.
categorize it as class 1, because the mid-infrared emission is, if it is increasing for the other source also,
Hmm.
then that will also contribute to this.
So again, that's what I said, like this categorization is a tentative and this is supported by this speculum SED here. The second point,
So at what wavelength? I mean, what wavelength range they did for individual or they did for?
so again, both.
So that's the point, you
that's the
can't
point.
use that.
Yeah,
You
exactly.
need to.
So the things are tentative, and that. So one thing, one point I would like to.
Yeah, it's simple.
So you can speak, you have a, that binary things
Yes.
as resolved, right?
Yes.
So do you have a multi-band data on the transpac?
No. So we have only one epoch of observation with telescope, and unfortunately only in J and K band. So that's
J and K band.
not H band. That's
No,
again.
no, on the G and H band you have a data.
Yeah.
From that you can have some idea about the individual sources.
How it is
Spectrum,
rising,
yes,
SED.
color.
The color-
So if you do that
Yeah.
PSF photometry, remove another
Ah.
one. Yes, so you have a.
So we try to do that actually. We
Yes.
try to do that,
Yes.
and we even try to fit some.
That will be one results, at least you have a means,
Uh-huh.
whatever that Aita is telling that Y's may not be direct.
Yes.
So only TransPec give you some details.
Yeah, I completely agree. I even tried with the J and K band of this telescopic
Yes.
image, but the results were that again I have showed this H and K color difference of the two objects.
Yeah,
These color differences are taken actually from the telescope only.
TransPec.
So they give an inference that the two sources are related in some way. Further observation of this source in the triopter band with the telescope will give a much better inference. And segregation of one of the source magnitude from the other by having some image manipulation technique in the optical and
Distance came from where?
so the distance to this source.
Yeah.
So basically from the kinematical study of the CO on the lines.
Gaia is detected.
I didn't.
Okay, we are running short of time.
Okay, we can.
Thank you, Kaustubh.
Thank
There is a small exchange now. So now before Prashant K and I will present and Mayank will after. A little exchange in between these. Thank you. This time is really 15 minutes. Have to finish.
Hello. 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 Yeah.
Good afternoon, everyone. So, myself Prasanto, I will talk about how we can use Galax data, which comes in the UV wavelength, and combine that with the Gaia data. We can identify new T-Tauri stars candidate, and once we identify those T-Tauri star candidates, then we can use ground-based telescope, mainly the spectroscopic data, to confirm whether they are classical or weak line T-Tauri stars. And in the later part of the talk, I will also discuss what are the future prospects of the DOT and how we can combine that with our space-based telescope UVIT to study the T-Tauri stars. So in this method where we are using Gaia and the Galax, the main thing comes is the UV axis in T-Tauri stars to differentiate the T-Tauri stars from the dwarf stars. So let's first discuss what's the origin of the UV emission in the T-Tauri stars. As you have already as you already seen in the previous talk,
The point is it's white.
okay, sir. So the UV emission in the T-Tauri stars mainly comes from the very central region where the material falls on to the stars from the circumferential disks through the magnetospheric accretion. And you have to note the point here that FUV and NUV, these emission comes from the different part of the accretion column. So FUV comes near the hotspot where the material directly hit the photosphere, and the NUV come just before that the piece of PGF. So this is the case for the classical T-Tauri, but for weak line T-Tauri where there is no accretion happening, the UV emission mainly comes from the chromospheric activities. So here, this is just a schematic diagram of a classical T-Tauri star. Now we know the UV emissions origin. Now, why we need to study the UV emission in T-Tauri star? What's the importance of that? It's because the UV is directly giving you the measure of the accretion properties or the accretion luminosity. While people usually use H alpha emission because it's difficult to get the UV observation because that you need space observation for that. However, we have lots of UV observation available in the galaxy, and we can use that to identify new candidates and at the same time studying their properties. Another fact you should note that the relation between the primary and the secondary indicators is not well established as well. And as you have seen in the last slide, the equivalent emission comes from the different part of the accuracy column. We need simultaneous observation for both. So here comes the galaxy, which gives you simultaneous equivalent energy observation, and Gaia gives you the proper motion and the distance to the molecular cloud so accurately that you can know which one is the proper member to that cloud. So we plan to use these two data, and then we combine the ground-based spectroscopic data to combine it. So for the sample selection, what I've done is that for first case, we have used the torus molecular cloud as a target, and later we thought of moving to other star forming regions. So we have used all the stars which have 100 to 200 parsec of distance using the Gaia, and having the and also use some astrometric. Sorry. Some of the astrometric part of comes from the Gaia, and then finally we have used the proper motion card to finally come up with the 51 number of objects which we found have the UV emission. Sorry, the UV observation. So before going to the what's the criteria we have given to separate the T Tauri stars, let's first look into what are the previously known T Tauri stars are present in the galaxy and where they actually located in the calorimetry diagram. So if you just look into this calorimetry diagram here, so I have just plotted in the gray all the stars falls in the 100 to 200% just to have an idea like how the CMB looks like. And on top of that, I have plotted the confirmed classical and weak-line T Tauri stars. You do see that everything falls on the pre-main sequence very nicely over here until you go to the UV CMD, where you see that all the stars which supposed to be in this sequence in the pre-main sequence move towards the white dwarf sequence. So you can clearly say that all the stars, at least most of the stars which are bluer than this red line, are the T Tauri stars candidates. Now just plot all those 51 stars over here. You can clearly see that there are only very few number of stars in the white dwarf sequence. While you will come in the UV part, there are so many stars over there. So if you just choose all the stars bluer than this red line, then you see that all these stars comes over here in the optical CMD, which is in the pre-main sequence stars. Now, what will be the candidates for the T Tauri stars? All these blue dotted points, which lies in optical in the pre-main sequence stars, what falls in the white dwarf sequence. So these are the final candidates. So we found 22 new candidates, and we have also retrieved 11 known previously T Tauri stars candidates. So now once you have this T Tauri stars candidate, actually from the CMD is very difficult to separate which one are the classical and which one are the weak-line T Tauri stars. So we have make a follow-up spectroscopy study for all these newly identified candidates, also along with the previously known one. So we have first went to the archive. We found 14 of Lamos. Then we have recently observed with transfer of 3 newly identified candidates, and from H1 we found 8. So here I have just shown you the example of classical T Tauri spectra of a classical T Tauri and how it differs from the weak-line T Tauri stars. You do see a change in the strength of the H alpha emission from classical to weak-line. You do see a similar example taken from the TAN spec. Here also you do see a large number of variation in the strength over here. So this is visually you can say, okay, there is a variation in the strength, but you also have to quantify them, and there is some relation to actually distinguish based on the strength of this line, whether it's a classical or weak-line one. So if you first calculate the equivalent width of all those stars, and then you plot in a spectral type versus equivalent width a diagram where this dotted and the blue lines actually separate the weak line and classical one. So for a particular type of spectral type, if you have equivalent width larger than the dotted or the blue line, then you call it as a classical one. So using this method, we have found that there are 7 weak-line T stars, there are 15 classical one, and you can see there are some T stars which falls just over the line which is separating these two classifications. So we say that we need further classification for these sources because we don't know whether these are varying in accretion, which may go up or down based on that. And another thing you should note down that there are 2 star marks I have made with the color one. These are previously classified as a weak line one, but we have reclassified them as the classical one that you said here. So once you have classified them, the next task is you have to have to calculate the parameter of those stars. Like as I said that you have a option to calculate the accretion luminosity from the UV observation, and you can compare that with the H alpha luminosity to say whether these are matching well with or not. While we are doing this calculation, we thought while we were using the Galaxy data, why not let's look into the archive of the UVIT. We found there are 6 T Tauri stars, which is already known from the previous classification. And they have been observed in both FUV and NUV, and that also in the multi band, because for UVIT we have 3 band in FUV and 3 and NUV. I just saw the preliminary result from the those sources which have the UVIT observation. So to estimate the parameters of this T Tauri star, what we use is the ECD analysis. So what I've done is that I've told you that the UV part of the accretion of the T Tauri stars mainly comes from the accretion or the chromospheric activity, and the optical part comes from the photosphere activity. So we try to model the UV and the optical by the dual fitting of the theoretical ACD. So for the UV part, we consider that it's a black body emission, and for optical we have used as it's a dwarf emission. So if you just look into these 2 plots where the left hand side is ACD of classical T Tauri stars and right hand side is well-known weak-line T Tauri stars, you do see the difference in the black body emission. So you see there is almost 10,000 black body emission is coming from the left hand side source FM tau. This clearly says that okay, this is due to the accretion, while you do see the very low amount of black body temperature over here. And if you also look into this ACD very carefully, you do see the excess amount of UV emission with respect to these dwarf stars over here and over here. So I just showed the analysis from the 6 T Tauri stars. So what we have done is that we have estimated the accretion luminosity, which mainly comes from the volumetric luminosity of the black body emission, and we have the equivalent width of H alpha, and that will give you the accretion luminosity from the H alpha. And we try to get some correlation over here. We have little larger error over here because there is less number of data points. When we include the Galaxy data, we hope we will get some better result over here. And yeah, we out of 22 new candidates, we are only able to take the spectroscopy follow-up of 14 of them, and out of the 14, the 7 we found the classical T Tauri stars. Now, you can think now that while you were using the Galaxy data, why not use the UV data for the further study of these T Tauri stars to photometry? The point is that NUV is not working in the UV. You won't get the simultaneous observation in FUV and NUV. But what you can get is the FUV spectra of those T Tauri stars for studying the T Tauri for the accretion properties of T Tauri stars. In the archive, what we found is a really interesting one. We found FUV spectra of TW Hydra. It's around 8 kilosecond of observation. It's a very fast spectra of T stars using UVIT, and you can clearly see the C4 line, helium, and the oxygen one, which are the indicator of the accretion in the classical T stars. Once you have this spectra, you will obviously look for whether the spectra is okay or not, how is the quality. So you compare it with the IV spectra. In the IV spectra, we found there are two epochs of observation. One epoch matches very well, while the other is slightly different. Also in the continuum. So it looks like there is variability present in this target, which maybe comes from the variation in the accretion. So can we able to see the variation through the UVIT? So for that, what we have done is that we have gone to the HST database where TW Hydra has been extensively studied, and here I just showed you the 3 epoch of observation, almost 1 day gap between them. This is a high resolution image, spectra. If you just degrade it to UVIT resolution, so these solid lines are the different dates of the HST observation, and then you do see that this nicely matches with the UVIT one. So from here I can say that yes, we can actually study the variability of the T stars, or the variability in the accretion of T stars with UVIT. And the nice thing about it is once you were using the UVIT, or in the upcoming mission INSIST, you can simultaneously observe the optical to IR spectra using TANSPEC to say that okay, how the accretion property is matches with the evolution of the disk property, where the optical and the NIR emission comes from the inner part of the disk. So here I will conclude.
So,
Yeah, very nice talk. So the double power law fit, where you're fitting a power law for double spectrum. Yeah, AC, double ACD filter. So I'm not very sure how well you are constraining the peak and the sort of downward thing. So my comment, or just a thought, can you get the blue band excess also in the optical spectra? So dark level spectroscopy will be available for this region. So can you get the veiling parameter, and will it be constraining better if you have a blue band excess also there?
Yeah, if we include veiling, that will obviously do the better one. But for this purpose, we are not including. So I've done some literature study. They says there is not much veiling for these sources, but yeah, we can include.
Okay. Oh, there is no veiling.
Yeah, this is very less actually.
Oh, okay. Yeah, very interesting.
Sorry.
I was curious about that white dwarf and T-Tauri overlap.
Yeah.
And particularly, I think also you showed that some HL. Okay, first is this. There are some in the left-hand side. There are some blue points, right?
Yeah.
They are FUV bright. You're still calling them as.
No. These.
You are not calling them as. You are removing them.
Yeah. These are most probably the white dwarfs in the Taurus monitor cloud.
Okay.
But that also got surprised, like this many number of white dwarfs, which is not.
But distance-wise, you can check with the.
Distance-wise is okay. Proper motion is also it's okay. So the distance, proper motion, everything says.
They are right.
It has to be in the Taurus monitor.
In the Taurus, I see. Okay.
So
That's interesting.
Quite interesting.
First thing. And second is about these other points. Why do they come? I'm just curious about that.
Why do this one?
Yeah, no. Then once in optical they appear in the T-Tauri, but they move, they become very bright and appear to overlap with the white dwarf regime in the UV color diagram. That is obviously because of the UV excess.
Yeah, true.
Yeah, but that is not very well modeled. I think UV excess in most stars is not modeled because of.
Yeah, true. So that's what our actually main goal for this.
Okay.
So we have lost
another small question.
just
Yeah.
last.
Yeah. So you had one. You showed spectra of classical and H alpha, I think. No, another one where you show the profile. Yeah, so the V plan shows a very broad.
No. This is
not correct.
This is not. Yeah.
No, it's not normalized.
This is not normalized. So here somewhere which alpha supposed to come.
No, I'm not talking about that. I'm talking about width also.
This one, right?
Oh, okay.
No. This is. Yeah.
I
I just
see.
saw it.
So Prashant, you should say that.
Yeah.
I was like, what is happening?
Okay, thank you. Let's thank the speaker. Now next is Mayank.
Top pointer, mid forward,
And
bottom is backward.
So, hello everyone, I am Mayank Narang from the Tata Institute of Fundamental Research. I'm a final year student now. So the first talk I ever gave in my PhD career was at SPF 2016. And it's pretty fitting that perhaps the last talk I gave in my PhD career at TFR is also at SPF 2022. So that's almost 6 years now. So the title of my talk is Unveiling the Photospheres of Protostars with Gaia and DOT. So I have a lot of collaborators. These are the names. So the talk is basically going to focus on trying to detect the photospheres of protostars at optical wavelengths.
Listen, contribute twice.
Oh.
More credit. Double.
Okay, so let's jump into the talk and the meat of the talk. So before we talk about detecting optical protostars at optical wavelengths and their photospheres, let's see why we want to study the optical protostars at optical wavelengths. So one of the fundamental questions in star formation is, when does the photosphere first form? And the best way to actually detect photosphere is using optical and near infrared spectroscopy. And this has been long done for pre-main sequence stars and even main sequence stars. However, the detection of photospheric features at optical wavelengths for protostars has not been very well done. There are only a handful of examples where the photospheres of even spectra at optical wavelengths for protostars has been taken. So in this talk, our main aim is to actually increase that number of optically detected protostars. The other reason why we are interested in using optical wavelength to detect protostars is because the direct accretion tracers such as H beta, H alpha, calcium IR triplet all fall in the optical wavelength, and also lines like passion beta, bracket gamma are in the near infrared, which can be readily accessed by instruments like Transpect and H-force and ANT-force. So, but however, due to the large line of sight extension towards protostars, they're typically not seen at optical wavelengths. However, deep surveys with telescopes like Gaia can actually reveal them. And to do this, I actually started a pilot program where we looked at protostars in the Orion star forming region from the Herschel Orion Protostellar Survey, or HOPS. So the HOPS team detected 330 protostars in Orion, 92 of them being class 0, 125 class 1, 102 class spectrum sources, and there were also some class 2 sources detected in the survey. So here I'm showing the survey coverage. So we are basically looking at Orion A and B molecular cloud with the blue ones showing the location of the protostars, and I'll come to the red ones at a later stage. Basically, the red ones are the ones which we detect with optical wavelength with Gaia. So to actually detect these protostars at optical wavelength, I use the latest Gaia catalog, that is Gaia EDR3, and I use the search radius of 2 arc seconds to search around the IR position of the protostars. So the IR position is from IRAC 2, 3, and MIPS, and I used a search radius of 2 arc seconds, and we actually found about 62 counterparts to the 330 protostars in Orion within 1.3 arc seconds. The first question that might come to your mind, and that also came to our mind, was whether what we were seeing were actually protostars at optical wavelengths, or were there some background or foreground targets?
So to check this hypothesis, we actually obtained the ALMA 870 micron images from the Van Dam survey. So we actually found that the median offset between the ALMA position, so basically by fitting the ALMA observation with the 2D Gaussian and the Gaia position, which is obtained from the EDR3 catalog, they are within 0.1 arcsecond of each other, indicating that indeed what we were detecting were protostars at optical wavelengths. So here you can actually see nicely some of the protostars. So you see the black represents the Gaia position, the red represents the ALMA position, and they're almost overlapping. And in the case of HOPS3, they're more or less there as well. So indicating that indeed what we were detecting were protostars at optical wavelengths. And surprisingly, in our survey, two of the protostars, that is HOPS 65 and 163, we find that they have a disk morphology which is very reminiscent of transitional disks. So transitional disks are disks which have large gaps and holes carved out in them. And it is thought that these transitional disks, the gaps and holes are carved out by planet formation. But what we are seeing is in protostars, which might be few 100,000 years old, they already have these gaps and holes forming in them. This perhaps indicates either two things. Either planet formation starts very early on in the protostellar life, even starts on very early in the stellar lifetime during the protostellar phase, or significant disk evolution at least happens during the protostellar lifetime. So with this, let's see why we detected these protostars at optical wavelengths and how these protostars are different from the parent sample. So first, let's compare the bolometric luminosity, that is the entire luminosity of the protostars at between the master HOPS sample, which is shown in blue, and the Gaia EDR3 detected sample, which is shown as peach. And we find that the HOPS master sample and the Gaia detected protostars, they have similar bolometric luminosity. While if you look at the bolometric temperature of these two objects, again, the parent sample is shown in blue, whereas the Gaia detected sample is shown in peach. We find that the bolometric temperature of the optically detected sources is much higher, indicating that they are more evolved sources. So higher bolometric temperature means a more evolved source, and that is what we are finding. This is also evident if you look at the evolutionary stages of the protostars that we detect. We don't detect any class 0 protostar. We detect about 18 class 1 protostars and about 36 flat spectrum protostars, indicating that Gaia is preferentially detecting more evolved sources. So in literature, there are two competing hypotheses as to why we should be able to detect protostars at optical wavelengths. It could either be that they have a small envelope such that the envelope mass is tenuous and the line of sight towards them is less. So we check this hypothesis by computing the envelope mass of these protostars, and we find that the Gaia detected protostars have a smaller envelope mass than the parent sample. The other hypothesis that we explored and that was given in literature is that if the inclination angle of the protostars is such that we can see through the cavity onto the photosphere, then also we should be able to detect them at optical wavelengths. So we also obtain the inclination angle of these protostars. We use again the Van Dam data, and we use the semi-minor to the semi-major axis as a proxy for the cos of the inclination angle, which we can then use to compute the inclination angle. And we find that the Gaia detected sources have no preference to either be face on or edge on, indicating that it's perhaps due to a tenuous envelope and not due to a favorable geometry that we are detecting these protostars at optical wavelengths. Since some of these protostars are actually bright, with the brightest ones being about 13 to 14 magnitudes in G band, we were also able to follow them up with using spectroscopy, using several Indian facilities such as the Aries Deostal faint object spectrograph on DOT 3.6 DOT and the Himalayan faint object spectrograph on camera H4s on HCT. So for 18 protostars, we were actually able to get their optical spectra. So here I'm showing you the case of two protostars, HOPS 58 and 235. Both of them have very similar protostellar properties, L-bore of 4.5 versus L-bore of 4.8, T-bore of 620 versus T-bore of 680. So both of them essentially have very similar protostellar properties. But if you look at the spectra, and I want you to concentrate here, there's a titanium oxide band in case of HOPS 58, while we don't see any such broadband absorption feature in the case of HOPS 235, indicating that perhaps in the case of HOPS 58, we have basically definitely formed the photosphere, and the photosphere most likely is a late to early type M-DOF, while in the case of HOPS 235, it could either be that the source is a more massive star, or a more massive star is forming at the center, or perhaps that the photosphere has not been formed. So from the 18 protostars for which we had obtained the optical spectra, 4 of them show this titanium oxide feature, indicating that the photosphere starts perhaps forming as early as in the class 1 flat spectrum phase. We further computed the mass accretion rate onto these protostars using the H alpha line. So we have region of strong H alpha line from these protostars, and we find that the mass accretion rate is actually on the lower side of the order of 10 to the power minus 7 to 10 to the power minus 8 solar masses per year. Such kind of mass accretion rates are also seen in T Tauri stars, indicating that either most of the matter on the protostar is accreted during the class 0 phase, or that variable accretion is the dominant phase, dominant mode of mass accretion. And we're just seeing these protostars perhaps at the quiescent phase. So one of the advantages of this in a current decade is the advent of the digital optical telescope and the instrument Tanspec, such that we can get we can actually get a simultaneous optical to NIR coverage. So we are not just limited to from the case of HCDNA. So we have to do 2 separate observations and then switch over to another instrument. We can actually get simultaneously observations from optical to all the way to K-band. So here I'm showing the Tanspec observations for HOPS 134. So it's a flat spectrum source with a volumetric luminosity of about 8 solar luminosities and a temperature of about 780 Kelvin. So we see strong H alpha accretion line in the optical with the strong calcium IR triplet and the Passion 19 line also seen around the 8,500 angstrom regime. We also see several other Passion lines as well as we also see the helium line as well as the Passion delta, Passion gamma, Passion beta, which is also you can see as I'm going further. We also detect some of the forbidden iron lines in the edge band. We also detect strong bracket gamma from the source. So Tanspec can actually allow us to study the entire, at least the near infrared to optical mass accretion indicators and outflow indicators simultaneously in one shot. So these were observations which were carried. So this is about a K10 kind of magnitude target, which we observed for about 45 minutes of total integration. And you can see that we are able to actually detect several strong lines in the spectra. So with this, I'll actually conclude my talk. So we started out with the question that can we probe the photospheres of protostars at optical wavelengths? And the answer to that question was yes. Using Gaia and follow-up studies with Tanspec, H-force, and AT-force, we were able to probe the photospheric properties of some of the protostars. So we detected 62 out of 330 protostars at optical wavelengths from in Orion. This increases the number of optically detected protostars by a factor of 3. So the previously about only 20 protostars were known at optical wavelengths, and now we have increased that number with 60. So that's a 3-fold increase in the number of protostars that detected at optical wavelengths. We find that the optically detected protostars are also more evolved, having a higher volumetric temperature and lower envelope mass than the parent sample. The detection of photospheres, the titanium oxide feature in 4 out of 18 protostellar spectra indicates that the photospheres can form very early on, perhaps in the class 1 flat spectrum phase. And the low mass accretion rate, as I stated earlier, of the order of 10 to the power minus 7 to 10 to the power minus 8 solar masses per year, which is similar to T Tauri, suggests that either episodic accretion is the dominant phase of accretion, or that most of the matter gets accreted pretty early on in the stellar life. And with this, end my talk. Thank you.
Yes, any question, please?
Nice. So yeah, I have a doubt for these class 1 sources, which are generally categorized as protostars. And here you are mentioning about optically visible protostars. Is there any particular criteria within this class 1 sources so that we can classify which are optically visible, like H alpha, the equivalent with cut or something?
I think it would be more easier if you can define it in terms of perhaps the envelope mass. So again, the envelope mass is slightly on the lower side. So it's perhaps the envelope mass which would be a better criteria rather than H alpha. Because even if you're detecting H alpha luminosity, that means you're detecting it at optical wavelengths. So perhaps the envelope mass might be a better criteria to distinguish between whether you can detect it at optical wavelengths or not. But again, you see that there's a large overlap between the two, the parent sample as well as the optically detected protostars. So perhaps it's not very easy to just by looking at whether you can differentiate between two or not.
So one more thing, what is the mass accretion rate for actual protostars? Here you showed that low mass accretion rate.
That is something that we don't really have a good handle on. So like other studies also have found, like for at least the class 1 class spectrum phase, the mass accretion rates are on the lower side. But used.
Which one?
Yes, I can.
Okay. So just keep these two separate. This is forward. And this is backward, downward, and pointing is top.
Good morning, everyone. I'm Belinda Damien. I'm a PhD student at Christ University with Professor Katie Paul and Dr. Jesse Jones. So in this talk, I'll be discussing a novel technique that we have used to identify low mass stars and substellar objects using the water band filter. A brief about this work was presented by Dr. Jesse in her talk. So here I'll be discussing more details about the work. So to begin with, I'll first briefly explain what substellar objects are and how we have used the water band imaging technique to identify these brown dwarfs, and finally present some results about our work in Sigma Orionis. Okay, so what are brown dwarfs or substellar objects? So we know that an object that burns the common isotope of hydrogen in its core is termed as a star, and those below the hydrogen burning mass limit of 0.072 solar mass and the ones which burn deuterium are called as brown dwarfs or failed stars. And the mass range for brown dwarfs is between 72 to 13 Jupiter mass. And objects below the deuterium burning mass limit are further classified into two. If they orbit a star, then they're called as planets. And if they are free floating, they're called as isolated planetary mass objects or sub-brown dwarfs. Now, since brown dwarfs do not have a continuing nuclear energy source in their core, their evolution is a process of cooling with decreasing luminosity with age. So young star-forming regions will be the ideal sites to detect these brown dwarfs, which are brightest during their early stages of evolution. So why is it important to study brown dwarfs or substellar objects for the matter? Firstly, as I mentioned, brown dwarfs have a mass range between that of stars and planets with temperatures below 3000 Kelvin. So they kind of form a bridge between these two classes of objects. In fact, when we look at their cool atmospheres, it is a boon that brown dwarfs are so similar to giant planets. Since direct imaging of exoplanets is difficult due to the obscuring light from the central host star, understanding brown dwarfs will aid in understanding the properties of exoplanets. Secondly, their formation scenario. So we know the basic mechanism for Loma star formation, where stars form by the gravitational collapse of the molecular cloud, whereas on the other hand, planets form by the accumulation of planetesimals in the circumstellar disk around the central protostar. But when we look at brown dwarfs, there are various formation theories that have been proposed, like turbulent fragmentation, which suggests that brown dwarfs form like Loma stars through dynamical ejection from multiple systems, formation through disk fragmentation, which suggests that brown dwarfs form like planets, and also formation through external photoerosion. So there are various mechanisms which have been theorized for the formation of brown dwarfs, but there is no consensus as to which is the dominant mechanism which aids in the formation of these low-mass objects. Another major importance for carrying out this study is to explore the low-mass end of the IMF. So IMF, or the initial mass function as we know, is the distribution of stellar mass at birth. So there are various functional forms which have been formulated for the high mass end of the IMF, mainly above 1 solar mass, following the pioneering work by Salpeter in 1955. But as we move towards the low mass end, the substar IMF is not well constrained. This is due to the paucity of data due to unresolved multiplicity, and also due to dependence on estimating the mass based on various stellar evolutionary models. So to understand a star forming event and its dependence on the environment, we need a better understanding of the IMF, for which we need the complete census of the substellar objects in the region. So these are some of the key factors which motivate us to carry out a study on these objects. Moving on, now I would like to address the question of how do we detect these objects. So canonical approaches towards substellar studies rely on photometric identification and then followed by spectroscopic classification, which demands a significant telescope time. However, identifying these low mass objects and distinguishing them from the reddened background stars are quite difficult. So we need an effective approach where we search for these young low mass objects via unique spectral features like the water absorption feature that is significant in cool late type objects. So here in the figure on the left, so this shows the spectra and photometry of two objects. One is a reddened background object, which is shown in red, and the other is a young M9 brown dwarf in the row of Fucus star forming region, which is shown in blue. So now if we see the broadband colors, now if we look at the broadband colors of these two objects, they are almost indistinguishable despite having a different underlying spectra. So now what we have done is we introduce a custom narrow waterband filter, or the W band, which is shown in yellow. So this W band filter breaks this degeneracy between the two objects, that is the reddened background star, which does not have water absorption, and the young brown dwarf, which has deep water absorption feature in its spectrum. So by combining the waterband filter photometry along with the broadband GNH photometric data and using it in the relation given here, which is the Q index, we can identify these brown dwarf objects photometrically. So the figure on the right shows the Q index as a function of spectral type. So spectral type is a proxy for effective temperature and mass. So from this, we see that objects which are later than M6 spectral type have a Q index value of -0.6. So we use this Q index value to further photometrically identify the brown dwarfs. So this work was done as part of a large W-band team, which surveys different star forming regions in solar neighborhood using the custom waterband filter in Wirecam on the 3.6 meter Canada France Hawaii telescope. So this is the largest and the deepest survey of star forming regions within 500 parsec in search of young planetary mass objects with sensitivities down to almost 3 Jupiter mass. These are some of the regions that the team has surveyed. And now I'll be discussing some key results of my work on Sigma Orionis, which is soon to be submitted. So Sigma Orionis is a young star-forming region of age about 3 million years, located at a distance of approximately 400 parsec in the Ori-OB1b association, which is also commonly known as the Orion belt. This region has a very low extinction value of AV less than almost 0.2 magnitude. So these physical parameters make Sigma Orion ideal target to hunt for these brown dwarfs and planetary Mars objects. So now to observe the brown dwarfs, first we photometrically identify them using a criterion that is a Q index less than minus 0.6 plus 3 sigma. So this essentially segregates the objects with spectral type M6 and later. So that is the stellar and substellar boundary limit. So these objects are highlighted here in red. So this is the initial sample that we have filtered out. And then for these objects, we look at their location in different color banding diagrams, both optical and near infrared. So in the CMD on the right, we see that the initial sample of brown dwarfs here, some of them are lying along the field sequence. So these are some of the field contaminants. So we exclude them. And for the remaining brown dwarf candidates, we then look at their astrometry, if they are consistent with that of the Sigma Ori cluster, using the Gaia DR3 data. So this way, we filtered out 17 candidate brown dwarfs, which are highlighted here in blue. So for these objects, these have not been spectroscopically studied before. So for them, we did spectroscopic follow-up observations with the 3.2 meter NASA infrared telescope facility and the SPECS instrument. And we reduced the data, and we also did the spectral typing for these targets. So the image on the right shows a sample of one of the targets which we observed with IRTF. The spectra is shown in black. And on top of that, I have also, for the spectral classification, I used standard spectral templates. So here in this plot, I have overplotted the 3 best fitting red end spectral templates which match with the target spectra. So the spectral type for this object comes up to be M6.5 with a peaky H-band feature. So this is a characteristic feature of brown dwarfs. This is due to the strong water absorption here at 1.45 micron. So we see a triangular or a peaky H-band media spectrum. So for all of the candidates that we observed with IRTF, they have been found to be brown dwarfs, giving us a 100% confirmation rate for this region. I would also like to mention that we identified 5 more candidate brown dwarfs using our technique, but these were very faint to be observed with the 4 meter class telescope. So we have proposed to spectroscopically identify them with Gemini. And yeah, I would like to conclude with this slide. So the main aim of our study was to get a complete list of spectroscopically confirmed members in Sigma Ori and then build the initial mass function. So here I have shown the initial mass function in this plot, which are the black points with the corresponding error bars. This is the first time that we are probing the IMF down to the planetary mass regime for this region. So we have a range of between 19 solar mass down to almost 3 Jupiter mass. And overplotted on that is the log normal fit, which is shown in black. So the log normal fit gives a characteristic peak mass of 0.23 and a sigma of 0.46, which is consistent with the other young star forming regions. And I've also plotted a segmented power law, which is shown here by the dotted line. So we see this has a break mass of 0.27 solar mass. So we see that the power law fit for the substellar IMF is describes the distribution in a better way than the log normal fit. Also, we get the brown dwarf to star ratio to be around 0.24. That is 4 stars for every brown dwarf in the region. And our conclusion is that the IMF for this region in comparison to the IMF for different star forming regions in diverse environments shows that the shape of the IMF is largely insensitive to the environment in which it is present. These are the conclusions of the work. We have also submitted a HST proposal to carry out a similar analysis like the water band imaging for a distant star forming region at 2 kiloparsec, and various other proposals with GTC, Gemini, and IRTF for future work.
Manoj.
Nice work, Govinda. You said you had surveyed a few star-forming regions with CFHT to identify the, yeah. So what's the number of free-floating planets, I mean, less than 13 Jupiter mass that you identified in these regions typically?
I can talk about this region which I have worked on. So for Sigma Orion, less than 30, what is it?
30?
No, we wanted for 30 Jupiters.
Less than 13, I mean, the
Planetary mass,
yeah,
okay.
yeah.
So less than
How
70,
many?
we have around 45 sources. And if we go down to less than 10 Jupiter mass, it's around 11 sources.
And do you know the number for the other sources, other regions? No, I'm asking this because there's recently a paper by the team led by Motohide Tamura. In Upper Scorpius, they have identified more than 100 free-floating planets, and in Taurus, another 100 or so. So these are huge numbers, and that's not using W band. It's just normal, imaging, deep imaging with Subaru. So I was just wondering, how does this compare? So, the numbers are low on your, in your case. So this raises the question of completeness and other things.
Okay, so one thing I would like to mention
Yeah,
is
the
that
IMF talking about IMF establishment. Yeah, so I just, that was the question. How do you compare it with this? You're aware of this work? It's published in the Nature Astronomy recently. There are more than 100 FFPs and free-floating planets. So,
but with Sigma Orion, we are actually complete down to the entire. So we have our CFHT detection.
yeah, complete in maybe in one region that you pointed, but
Yeah, because the Sigma Orion is a very small region in terms of area.
no, but it looks as if in Taurus out of 900.
Taurus is a large region.
Yeah.
So you have, obviously you have more number of sources.
No, what I'm saying is 10% of the total population is FFPs.
Mhm.
So one has to be careful about that. I'm saying, I mean, we may be underestimating.
So your definition for that equation, you had a small e.
Yes.
Yeah, so my question is what all that E depends on what all factors?
So E is basically the ratio of extinction in the JH and W filters.
So that extinction is you are talking about industrial extinction or something atmospheric local?
Extinction in these particular filters. You have used the JH and W filters. So the ratio of extinction of those.
No, so extinction is due to what? That was my question. Is it you are talking about in the astronomical extinction or is local Earth's atmosphere, the things you are observing?
No, this is industrial extinction.
So day-to-day variation of water content or other things don't go into this E factor.
No, not into this. The telluric lines.
So
What is this 4 result per, like 4 WD per you give number of stars per sample? So how do you calculate? Like 4 stars in the last slide. How many like ratio, like how many WD?
Oh, brown dwarf to star ratio.
Yeah.
Okay, so this is basically brown dwarf is between this mass limit, deuterium burning to hydrogen burning mass limit.
So how do you know that your sample is complete, and how do you know that your ground detection is complete?
So excluding this IRTF sample, I have also surveyed the entire CFHT data for 22 cross 22 accurate area. This includes the previous studied spectroscopically confirmed members as well. So
No, so filter end you will have less detection by your like procedure.
So maybe I can add, so photometrically we are complete because it's a deepest observation. So, but we are looking at a still magnitude, right?
No, your scatter is higher with lower end, like 90, 20, 21, and your detection is low.
So that's how the region, but photometrically we are complete down to 21 magnitude. If you go with the completeness factors like that star.
So detection in brighter end is higher and filter end is lower by this plot. You can see. The ratio of number 4 is like 4 drop. For every 4 stars, you have 1 drop. But if you go from bright to F, this number is going to change. No.
Yeah, so we have the photometry completeness down to 21 magnitude for this state. So in that sense, we are sure that it's a complete sample.
Very nice talk. Actually, I am curious to know that I newly proposed round of you observe with the spectroscopically or
No, these five we couldn't observe because our IRTF detection limit went up to only 17.5 now.
okay.
So we did higher class telescopes.
Then another things, sigma would is some prior round of already spectra is there.
Yes.
So have you cross-checked all the your W dates, whatever is coming? They are coming on this.
Yes, they are located here. So these which I have not marked, so these are
Yeah,
already
that's right. Yes.
spectroscopically known.
So we have already a few bona fide already
Yes.
candidates established in the sigma waves.
Yes.
So how are they are coming in the your W dates?
So they are all below the Q less than minus 0.61. So this is basically corresponding to M6
That's
spectrum.
okay, fine, but spectroscopically, whatever that we drive know these are brown drops from spectra. From
Okay,
other
yeah.
spectra.
So
So how we feel here?
yes, so to validate that, we have
Yes.
actually done the observation for previously known members,
Yes,
but not for this region, but for Ophiuchus and IC348 we have done. And we get almost 80% confirmation rate for the previous one.
Yeah.
I have a quick question. You said that you match the astrometry with Gaia, right? So is Gaia really going down to 10?
So you said you match the astrometry with Gaia.
Mhm.
So is Gaia really complete up to 10 Jupiter masses? Isn't like the Gaia astrometry beyond 16 in G band, which roughly corresponds to like an M to M3. Beyond that, it's pretty bad. So how are you getting the astrometry for these brown dwarfs?
So the astrometry that I mentioned was for the IRTF targets that we observed. So that goes up to 17 magnitude region. So we take the astrometry from previously known members and we see if it matches with these new objects. That we
So how are you getting that astrometry? Is it from Gaia itself?
the Gaia parallax.
Parallax or astrometry? Astrometry includes proper motion.
No,
as
yeah,
well.
right. So proper motion we couldn't use because it is very low for this region. So we had to go with the parallax.
Yeah, Gaia, we are not complete with this limit. Yeah, whatever available, we check for their
Okay.
promotion, but whatever not available, we can.
So what was the mass limit up to which you were okay with Gaia? Do you have an answer? I'm just curious because
Yeah, she has a plot there, I think. But Gaia, we are not complete. Yeah. So,
Yeah, here. From 16.5 to 17 magnitude.
that's about 30 Jupiter masses.
Any one quick question?
No, I don't think Gaia is committed to
it's not complete, but there are detached. It's not complete.
Yeah.
Gaia is not complete.
Errors are
Okay, let's thank the speaker. Now this big lunch session is coming to end. Thanks to all speakers and the audience. Thank you.
Yeah, I have.
Do you have any announcement?
So
We have for tomorrow, we'll have two buses which will leave around 9 o'clock after breakfast, 9 or 9:15 o'clock to Houston. So we have around 45 people. So we'll be taking two tempo travelers and few of them have to go to Kargadam or other railway station. So we have six people: Sarita, Blesan, Sirja, Sridharan, Priya Hassan, and Nidhi Sabo. Other than that, they are coming back, right? So if I am missing anyone, please let me know. And also, these six have to put their luggage in the buses.
Also, how the city guys will go?
Yeah, this we are like we need the telephone number of that driver. So
Better to ask them to be in what case. Otherwise,
yeah, it will be better because to come here and then go back.
no, that is too much.
Okay. So we'll ask the driver's number. So because the other tempo traveler, we don't know who is coming. So
We will go via Kalita.
Yeah, yeah.
No point coming here.
Okay.
So even in a town, we can.
Yeah, but they will miss how they will do their breakfast. Yeah, yeah. So you can come if you like come to areas also, and if somebody wants to stay there, they can stay there. So I'll provide the telephone number and then they will call
It's
you.
one time, not 9 or 9:50. Just it will become.
Okay. Yeah. Yeah. Sure.
Say
So
9,
If we are coming here, we reach here at 9.
yeah. So yeah. So they yeah 15 or 20 minutes.
No, but as he's saying, if you're going that way, we find something there and have breakfast, it is easier, and then we catch bus at 9:15.
Yeah.
What kind to be expected to
Yeah, 9:30. 9:30.
Yes, sir, clearly announced, a lot of confusion. Say where the bus will be.
So it's 9 a.m. at Aries. The plan is that it will start from 9 a.m. But people have to take breakfast, so it will delay by 15 minutes maybe. So 9:15 from here.
We are already getting breakfast in our.
Yeah, so a few of them will come, and if they want to come, 9:15 the bus will leave from here, and it will take 20 minutes to reach the lift. So 9:30, 9:35. So people have to be
So
there.
that option still exists of us getting our luggage, having breakfast in 15 minutes and go back.
Yeah,
Option
yeah,
exists.
yeah. So 9:15, that's why.
बस नहीं है क्या? 8:30
So 9:15 we are leaving here. So
8:30 बस है कि नहीं?
है. It's regular bus.
Regular.
Yes.
Okay, we are getting breakfast.
Then fine, then why, what's the problem then? If you are regular.
No, some of us are not getting. No, so we getting put the luggage up there, फिर आग घूमता ही रहना है ऊपर नीचे.
So I have to come here and go back.
Yeah. लेकिन हमें ढूंढना पड़ेगा. I don't even
Hey,
know.
come on. Hey, come on.
वहाँ पे बहुत है.
One more
साया में सब पूरा है.
But it's not. It's a smaller than the.
हाँ, तो वो अलग है. तो अगर going back